In this video, we will take a look at the first come first served scheduling algorithm. In short, it is known as FCFS. So we know that scheduling refers to allocating the CPU to a process in the ready queue. So FCFS will schedule the process in the order in which they arrive in the ready queue. This algorithm is very easy to implement, as we will see, but it is poor in performance due to high waiting times. And this is primarily a non-preemptive scheduling algorithm. What is non-preemptive? You can check my earlier video on this. But FCFS can also be implemented as a preemptive algorithm, but primarily it is a non-preemptive scheduling algorithm. So let's take an example, and through this example we will understand how this algorithm works. So assume that 5 processes P1, P2, P3, P4, P5, they arrived in the system and these were their arrival times. And the burst time is also given. And when we are talking about the burst time, we are referring to the CPU burst time. That means for how much time units a particular process will require the CPU. Now since we are implementing the first come first serve, that means whichever process arrived first in the ready queue will be allocated the CPU first. So as you can see, if we check the arrival times, this process P4, its arrival time was 0, followed by, if we draw the ready queue, so P4 arrived at 0, followed by P3 at time 1, then P1 at time 2, at 3 no process had arrived, at 4 P5, and at 5 process P2 had arrived. So this is what our ready queue looks like, and the first process to arrive is P4. So let's start with time 0. What we are going to draw is a Gantt chart which specifies the timeline of the execution of the processes on the CPU. So we know that at time 0 there was only one process P4 in the system. So P4 is given the process first. Since this is a non-preemptive algorithm, even though P3 has come at 1 and P1 has come at 2, but P4 will be continually executing on the CPU. So since the burst time of P4 is 3 time units, it requires the CPU for 3 time units. So it will release the CPU at 3 time units. After that, the next in the ready queue, because we are following FCFS, the next in the ready queue is P3. So P3 will be given the CPU. P3 will run for 8 time units. So from 3 to 11, P3 will be using the CPU. At 11, P3 will release and the next in line is P1. So P1 will be given the CPU. The burst time of P1 is 6. So P1 will run from 11 to 17 and release the CPU at 17. After that, in the queue, we have P5 which arrived at time 4. So it is waiting in the ready queue. And now P5 is given the CPU. Burst time of P5 is 4. So from 17 to 21, P5 will execute and then the CPU will be allocated to P2, which has a burst time of 2. So from 21 to 23, P2 will use the CPU. So this is the Gantt chart. It shows the timeline of the execution of the different processes on the CPU. Now let's compute the various we will check the various performance metrics and see how the system is performing with this example. So this was the Gantt chart that we had drawn earlier, and now we will compute the waiting time for each process. Let's start with P1. P1 got the CPU at time unit 11 and its arrival time was 2. So from 2 to 11 it was waiting in the ready queue. So its wait time was 11 minus 2, which is 9 time units. P2 got the CPU at time 21 and it had arrived in the system at time 5. So its waiting time is 21 minus 5, 16. From 5 to 21, it was waiting in the ready queue. Similarly for P3, we see that it got the CPU at 3 and it arrived at 1. So its waiting time was 2. For P4, it arrived in the system at 0 and it got the CPU also at 0. So it did not have to wait at all. And for P5, it got the system at 17 and it arrived at 4. So wait time was 13. Now if we add all these wait times, 9 plus 16 plus 2 plus 0 plus 13, and divide it by the number of processes, so we will get 8. This is the average wait time for this particular example. Now let's compute the turnaround time. We had seen earlier that turnaround time means the time at which it came in the ready queue and it terminated. So assume that each process required only one CPU burst. So if this was the only CPU burst required and it terminated after that, if that is the scenario, then we know that P1 terminated at 17 and it arrived at time unit 2. So 17 minus 2 will be 15. P2 terminated at 23 and it had arrived at time unit 5. So 23 minus 5 is 18. And similarly, we can compute for P3, P4 and P5 also. Now when we compute the average turnaround time, so it will be 15 plus 18 plus 10 plus 3 plus 17. We take the turnaround time for all the processes divided by the number of processes and we get the average turnaround time. This is assuming that the processes are arriving at this time and finishing after this burst time, because turnaround time means when the process has terminated. Now the average waiting time in the FCFS scheduling may vary substantially if the CPU burst time of the processes is varying greatly. So assume that there is one CPU bound process and many input output bound processes. Like we know, say assume that P1 is a CPU bound process and P2, P3 are IO bound processes. In one of my earlier videos, I had explained this, that CPU bound process means it will require CPU for a longer period of time and a very short IO. IO bound processes means that they will require the CPU for a very short duration but spend most of their time doing IO. So we are assuming that P1 is a CPU bound process. That means its burst time of P1 is going to be much larger than the burst time of process P2 or process P3. So if P1 gets the CPU because it was the first in the queue to arrive and its burst time is large, so it will be using the CPU for a very long time. Meantime, the IO devices are sitting idle and P2 and P3 are waiting in the ready queue because CPU had been allocated to P1 and P1 is taking a very long time. Now suppose P1 finishes its execution on CPU and has gone for an IO. So it has come in the wait queue over here and now P3 will be given the CPU. P1 uses the IO and P3 uses the CPU. Now since P3 is an IO bound process, its burst time is very less. So quickly it will use the CPU and come in the queue here. Similarly, P2 was an IO bound process. It will also quickly finish its task on the CPU and come here. Now, when this happens, now the CPU is sitting idle. P1, when it finishes its IO, will go back into the ready queue and will be allocated the CPU again. By the time P2 and P3 come back to the ready queue, again they will be waiting because P1 is again using the CPU for a very long time. So, it always makes sense to have a mix of CPU bound and IO bound processes, but this FCFS becomes a problem if a CPU bound process is ahead in the line. So now all the other processes, they have to wait for one big process to get off the CPU. Since FCFS is a non-preemptive algorithm, till the time P1 is finished, all the processes will be waiting in the ready queue. So this results in lower CPU and device utilization than might be possible if shorter processes were allowed to go first. So if IO bound processes were allowed to go first, which were using the CPU for a very long time, then the wait time in the ready queue would decrease. This is referred to as the convoy effect. Convoy refers to a long trail of items waiting in the queue. So as we have just seen over here that FCFS leads to the convoy effect, because if a CPU bound process gets the CPU, other processes keep waiting in the ready queue.